I will basically talk a bit about advanced infrared spectroscopy techniques and how we can use them to study hydrogenases. For starters, I think we are all aware that when we're doing infrared spectroscopy on hydrogenases, we typically focus on the stretching vibration of the diatomic ligands at the catalytic metal side, as shown here exemplarily for nickel iron hydrogenases. And the reason for this is basically that these vibrations are very sensitive markers for the structural and electronic properties of the active site. Another thing that I think is important to highlight is that these, let's say, biologically uncommon and also catalytically important ligands were first detected by infrared spectroscopy, so about 25 to 30 years ago. And since then, infrared spectroscopy, I would say, has been a very important technique in hydrogenase research. Nevertheless, most of the time, I would say this technique has been applied in a type of, let's say, fingerprinting approach. And the reason for that is probably that it's not too easy or actually quite difficult to obtain de novo structural information from linear infrared absorption spectroscopy. For that reason, we basically decided to move on to nonlinear infrared techniques that basically retain the inherent advantages of infrared spectroscopy, but provide more insights into structure and dynamics. And to understand what nonlinear infrared spectroscopy actually is, we need to briefly also remember how we've performed a typical linear infrared absorption experiment. So basically, normally what you do is you basically shine continuous wave infrared radiation from an ordinary light source on your sample. And if the frequency of that light matches the frequency of a molecular vibration, you basically get a peak in your spectrum. And what you can do is you can also replace your ordinary light source with a laser source, and then use ultra-short infrared pulses to record your spectrum. Now, if you use just one pulse, what you get is very similar to a normal infrared absorption spectrum, so that's not too exciting. But if you use two pulses instead, you get a so-called infrared pump, infrared probe spectrum. And if you add another pulse, so 3 pulses in total, you get what we call a 2-dimensional infrared spectrum. So basically, the more pulses you add to your experimental sequence, the more signals you get in your spectra and the more information you can extract. So what kind of information is this? So very basically speaking, you can get detailed insights into solution phase structure, bond strengths, and so on and so forth, as you'll see. And in particular, we can also gain insights into different types of dynamic phenomena. We also typically complement this with computational tools that basically expand those insights that can be directly obtained from the experiment. With this introduction, let's have a look at what kind of information we can actually gain. And here we'll focus exemplarily on nickel iron hydrogenases, and in particular, those 3 studies listed down here. So just as a reminder, what we're looking at are the stretching vibrations of the 3 diatomic ligands at the active site. So this is one CO ligand, and then the 2 cyanide stretching vibrations. And if we start with the CO stretching, oh, sorry, that's what I forgot to mention. That's kind of important for what we're going to see. In a normal infrared absorption experiment, we particularly focus here on the fundamental transition, so between the vibration of ground state and the first excited state. So if we start with a CO stretching vibration, as shown here on the left, the infrared pump probe spectrum will basically look like this. So there's a whole bunch of signals now. First of all, we have a negative signal here at the fundamental frequency. So this basically corresponds to ground state bleaching and stimulated emission. And in addition, we also have these positive features here on the left, and they basically correspond to excited state absorption, in this case, up to the 4th vibrational level. What it means is basically that the higher we climb this vibrational level, the more strongly our bond is vibrating, so from a classical point of view. And that's quite interesting because the energies that we need to make it vibrate stronger will basically provide information about the bond we are looking at. So more specifically, in this particular case here, we can fit a so-called Morse potential to the experimental transition energies. And from this, we can extract a large number of bond strength descriptors that you cannot obtain from any other experimental technique in condensed phase. So for instance, we can extract the force constant, so that's basically the equilibrium strength of the bond. And we can have a look at the anemonicity, so that's basically the elasticity of the bond once we move away from the equilibrium bond length. And we can also get insights into the total bond length, so that's the dissociation energy. In addition, we can also use these quantities then, in particular the force constant, together with empirical models to gain insights into bond lengths. And what I would like to highlight here is basically that, of course, these bonds we're looking at here, in the case of the CO ligand, for instance, are very short. So we're just talking about 1 angstrom. And we can determine these bond lengths in principle very high resolution, as you can see. So at least as accurate as with the highest resolution crystal structures available at this moment. And so if you wrap this up, basically you can say that we can get a lot of detailed insights from pump probe spectroscopy into the bond properties of the CO ligand, which is, of course, important to understand how this unique ligand corresponds to the catalytic mechanism of the enzyme. There's one thing I have to admit, though, and this is that what I've shown you so far, where it's obtained from the pure state of the enzyme, more specifically this nickel active silence state shown here on the right. But things get much more messy when you look at a typical mixture of states, as you often observe for nickel iron hydrogens, because in that case, as you can see, there will basically a strong overlap of positive and negative signals, partial cancellation. And this is, of course, extremely problematic because it implies basically loss of information from your spectrum. What you can do in that case, though, is you can move on from pump probe spectroscopy towards 2-DAR spectroscopy, because in 2-DAR spectroscopy, signals from different redox structure states of the active site will basically be separated along the pump frequency axis. And so what you can do is basically you can just take horizontal slices to the 2-DAR spectrum, thereby extracting selectively the information that reflects a particular state of the enzyme. And then you just get this kind of like pump slice shown here on the left, which we can analyze in exactly the same way as I've just shown. Now, if you do this in this particular case here, you end up with the data shown here in the table at the bottom. And the first thing that you probably know is that when you move from the top of the table to the bottom, the vibration of frequency increases. And so from your general, let's say, physical chemistry textbook, for example, you say, oh, apparently the bond strength is increasing. Whether that's true or not will basically depend on what you understand by the term bond strength. So if you understand bond strength as the force constant, then you're absolutely right, as you can see from these entries here. This would probably be, let's say, general spectroscopist point of view of these aspects. However, most of the time, I'd say in chemistry in particular, we're not really interested in force constants because it simply just reflects the curvature of the potential energy surface at the very bottom of the well. But what we're really interested in is basically the total bond strength, so the dissociation energies. And if you look at the dissociation energies here, you can see that actually the values we get are pretty much the same. So there is no clear trend observable at all. And that's quite surprising. And the reason for that is basically that when we increase the force constant, apparently at the same time, the anomorphicity also increases. And what that means is that as long as you're very close to the bottom of the potential, so basically at equilibrium bond lengths, your bond gets very rigid or increasingly rigid. But at the same time, once you move away from equilibrium bond lengths, the potential gets very shallow. And so the overall bond strength doesn't really change. Now, we could assume that this may be something very special for this particular enzyme, but actually when you look into literature, for instance, on metal carbonide species in general, you can see similar things. So for instance, as I've highlighted here, you can see that there's may even be a reversion of the expected trend or relation between vibration of frequency and bond dissociation energy. This, I think, is quite important in general because it implies, at least for me, that we really need to think about what we mean by bond strengths, especially if you discuss it in the context of vibrational spectroscopy. All right, back to the data from hydrogenase. So apart from bond strengths, as I said before, we can also look at bond lengths. And that's quite important in this particular case here, because these data I'm showing here were obtained from a quite unique hydrogenase from the organism Hydrogenophilus termolitalis. And as you can see here, according to the crystal structure, the enzyme in the oxidized state has a very unusual coordination geometry. So here with a terminal bidentate glutamate ligand and then 3 instead of the typical 2 cysteines in the bridging position. And there's another thing that's interesting about the structure here, and this is that the CO bond length is very short, so clearly shorter than what you typically observe in crystal structures. And the value we see here matches very well with at least one of the 2 redox structure states we also observe in solution, and together with many other spectroscopic data, this basically allowed us to conclude that this kind of unusual geometry here is not some sort of crystallization artifact, but it's really actually something that you can also observe in solution, and it's actually functionally relevant for the oxygen stability of the enzyme. So apart from insights into bonding and structure, we can also gain insights into molecular dynamics, because the signals here in the pump probe spectrum are not static, but they are actually decaying as a function of time, as you can see here on the right-hand side. The reason for that is basically that after we excited, the bond vibration will also get damped after a while, again, classically speaking. And so we basically return from the vibration excited states back to the ground state. As you can see, this is happening extremely quickly here, so within less than 20 picoseconds. And this basically tells us that energy can be extremely quickly dissipated from the catalytic metal side towards the protein environment. And that's quite interesting for a couple of reasons. Inter alia, it shows that one of the fundamental assumptions in classical transition state theory, namely that all molecules that pass the transition state region become products and will never return to the EDOC well. And apparently, according to our data, this is also a valid statement, even though the active site is deeply buried inside the protein cavities without any contact to solvent molecules. Another thing that's interesting from this, according to these time traces here, is the fact that the time constants are actually all the same. So no matter from which of the vibrational states we're decaying, and this is in quite sharp contrast to what you normally expect and observe. And this basically prompted us to suggest that what we have here is a very specific energy transfer route towards the protein, so as opposed to normal dissipative undirected energy transfer. And there are actually some indications from this from our calculations. So we're doing anemone calculations here within the vibration and perturbation theory context or framework. And what we see from these calculations is basically that the CS stretching vibration we're probing here is actually coupled to a set of low frequency metal ligand vibrations, one example of which is shown here. And these low frequency metal ligand vibrations are then in turn coupled to the cyanide stretching vibrations, different types of nickel sulfur vibrations, and even carbon sulfur vibrations on the side chain. And so what we propose is basically, or it seems that these low frequency metal ligand vibrations, especially one shown here, also highlighted on the left-hand side, are quite more important to redistribute energy from this catalytic iron side towards the protein environment. So of course, we can not only look at the time evolution of the CS stretching vibration, but we can also do the same for the cyanide stretching vibrations. In general, we come to very similar conclusions regarding energy transfer. And in addition, we also see these very weird oscillations here on these decay curves, which are even better obvious if we remove the exponential background. Now, the reason that we see this so-called quantum beat pattern is basically that we're coherently exciting the enzyme. And so what we create is a so-called coherent superposition state. And to understand what is special about this state, you need to briefly remember that normally when we do an infrared experiment or any type of absorption experiment, we basically just populate energy eigenstates. So these are stationary states and they do not actually oscillate. They do not depend on time in a strict sense. By contrast, the superposition state actually does oscillate, and it does so with a frequency that corresponds to the difference between the excitation energies of the two vibrational modes we're looking at here. And this observation of the quantum beats is actually quite useful because if we observe quantum beats, we can basically conclude that the two cyanide stretching vibrations are actually anemonically coupled to each other. The reason being that quantum beats are only observed if the two excited states share a common ground state. In addition, what we can also do with these quantum beats is we can simply Fourier transform them, and then we get this kind of like quantum beat spectrum. And what you can see here is that for each pair of signals that correspond to a single redox state of the enzyme, of the active site more specifically, we get a single clear sharp peak in a quantum beat spectrum. And this is, of course, extremely helpful to assign signals and complex catalytic mixtures, as we often observe, as I mentioned, in hydrogenase. Last but not least, we can also have a look at the time evolution of the quantum beats, because as you can see, they also get damped as a function of time. This is what we call dephasing. And this is quite helpful as well, because it helps basically to understand the information encoded in the line width of the infrared spectrum. And the information, or the idea behind this, is basically the following. So if the dynamics in the, let's say, active site region of the enzyme was very fast, then we would say that we are in a so-called homogeneous limit. And within this homogeneous limit, there's basically a direct relation between the line width that we can measure and this dephasing time that we get here from the quantum beats. However, as you can see, if we would calculate the line width from the quantum beat dephasing time, we'd end up with a value that is very clearly different from what we observe in the experiment. And so we can basically conclude that we're not in this homogeneous limit, but we're rather in the inhomogeneous limit. And that's quite helpful because in the inhomogeneous limit, the line width directly reflects basically the distribution of structural microstates. So it's a marker for structural flexibility or the length scale of structural dynamics. Now, as we can see here, the line widths are very narrow, so just about 6 or 7 wave numbers. And this basically indicates that the active site and its environment is quite rigid. And this actually fits very nice to previous proposals that basically propose that the active site geometry, especially on the nickel side, is basically tuned by protein structure constraints. And if you don't believe the results from these spectroscopic and theoretical studies, we also have proof from crystal structures for that particular fact in the meantime. So far we have mainly looked at infrared palm probe spectroscopy and the properties of individual vibrations, or the information that we can extract from individual vibrations. But now we also want to go on to 2D IR spectroscopy and see what we can learn about the interaction of different vibration degrees of freedom. So first thing I show here on the left is just the 2D IR spectrum of the CO stretching vibration. So that's not too exciting. As you can see, it's basically the same peak that we also see in the palm probe spectrum, just in the two-dimensional representation, so that you can basically get a feeling how the spectra look like. But of course, we can also see signals in other parts of the spectrum, like the one shown here on the right-hand side, which is what we call the cross peak. And there are two important things about these type of signals. So first of all, as you can see, the excitation frequency is basically the same in both cases, so corresponding to the CO stretching vibration that we initially excite. But then the detection frequency is entirely different here for this cross peak on the right-hand side, now corresponding to this cyanide stretching vibration. The second thing that's important to note is that while these signals here on the left basically can be detected from earliest palm probe delay times on, these here basically grow into the spectrum as a function of the waiting time. And so basically what this tells us is that energy that we initially put into the carbon-oxygen bond at the negative side within a few tens of picoseconds is basically transferred to the carbon-nitrogen bonds. That may be kind of surprising because what we also know from 2D IR spectra is that the coupling between the CO and the cyanide is actually quite weak. And so what we propose is basically that the energy transfer actually occurs while these low frequency metal ligand vibrations that I mentioned before. So these findings I think are quite interesting because they basically show that you can use 2D IR spectroscopy to track the flow of energy through large molecules, like for instance hydrogenase. You can also use them to analyze, once again, complex catalytic reaction mixtures. The reason being that these type of cross peaks will typically only occur if the interacting vibrational groups are part of the same molecule. And in a similar sense, we can also use them to evaluate molecular structure, because typically the interacting vibrating groups do not only have to be part of the same molecule, but they also have to be in close spatial proximity. And we already actually used this criterion here in order to assign very unusually signals for the hydrogenase I mentioned before. And of course, all of this, I think, is quite interesting for studying complex catalytic systems, especially if you're interested in like non-classical aspects in catalysis, so where energy transfer could play an explicit role, or also allostatic relation and maybe other transfer of information processes and enzymes. So far we have looked at the interaction between the CO stretching vibration now with the cyanide stretching vibration. And the final part of the talk, I also want to have a look at what kind of information we can extract from the interaction between the two cyanide stretching vibrations, so the two individual CN stretch modes. And to this end, we will move on a bit towards computational 2D IR spectroscopy. And the first thing I'd like to highlight here is that, as you can see, in the calculations, we can very nicely reproduce the overall pattern of the enzyme. So we have the spectrum, which is of course extremely helpful to understand what we really see in the experiment and what kind of information we can extract. And this also transfers in particular to the cyanide stretching region, which is enlarged here. And there's two things I'd like to highlight in terms of the signature here. So first of all these spectra that we calculated were basically obtained from a very small first coordination sphere model of the active site. The reason being that these calculations are just awfully expensive in terms of computation time. And despite this kind of limitation, we can get the overall signature very well, as you can see. And this, I think, is a good indication that apparently the influence on the environment of the active site, especially the hydrogen bonds towards the cyanide ligands, may not be as important or significant for, let's say, the spectroscopic data as one might think. Another thing that I think is quite interesting here is that we have a very unique signature. So what you can see is we have a very small anomicity here for the symmetric cyanide stretching mode and a very large anomicity for the antisymmetric stretching mode. So that these two values are very different. And in addition, the two cyanide stretching modes are very strongly coupled. So 24 wave numbers is the coupling. This is pretty much in line with what we already saw for the quantum beat spectra. Another thing, or to understand what we can actually extract from these observations, from the very unusual signatures we see here, we then analyze these two quantities. So the difference in the two anomicities and also the coupling between the vibration modes for 3 different molar systems. So this is 2 cases. This is our catalytic immediates of the nickel iron active site. And then we also have this famous RNCP complex here. And the first thing that you can see is that these values are obviously not the same for the 3 different models we are looking at. And there's a clear correlation between them, which basically tells us that both the difference in anomicities and the coupling of the 2 vibrational modes are basically a measure for the interaction between the 2 cyanide stretching vibrations. Now, to understand what kind of information we can extract from these quantities, we need to briefly remember what kind of vibrations we actually look at. And as a first approximation, we typically say, okay, the low frequency mode is the antisymmetric stretching mode and the high frequency mode is the symmetric stretching mode. But this is still just an approximation. The reason being that the antisymmetric stretch is kind of localized on this cyanide ligand, while the symmetric stretch is kind of localized on the other cyanide ligand, which basically means these 2 cyanide ligands are not exactly identical. And the reason for that is that there's an inherent asymmetry in the nickel iron active site. Now, to quantify this localization of the 2 vibrational modes, we then calculated basically the scalar product between the normal mode vectors and an idealized bond stretch vector for the 2 individual cyanide ligands, as shown here on the right. And as you can see, if we move from the highly symmetric RNCP complex towards the nickel C state, basically mode localization increases. At the same time, we see that the interaction between the 2 vibrational modes decreases. The reason being that if the modes are more localized, then of course there's less spatial overlap between them, and so the interaction between them decreases. And that's quite nice because it basically means that we can use these 2 quantities here as a marker for the symmetry or asymmetry in the nickel iron active site. We can also further extend this analysis and use this fact to basically obtain local information about the 2 individual cyanide bonds from these multi-bond stretch vibrations, but I unfortunately don't have the time to explain this in detail. So with this, I'm basically at the end of my talk. I think I can kind of like skip the summary and just come to the conclusion. So I think with these new, let's say, nonlinear and ultra-fast infrared spectroscopic techniques, we can get detailed new insights into structure and dynamics, which provides new perspective, I would say, for understanding hydrogenases, other metalloenzymes, and basically also, let's say, multi-leveled macromolecular systems in general. With this, I basically want to thank then, of course, also all the people that have contributed to this work. So this, first of all, includes a couple of guys from the UK who were involved in the experiments I've shown here that were performed at the SFC Central Laser Facility in Harwell. Then, of course, I'm also very thankful to everyone who has provided samples for these studies or helped to prepare them. And last but not least, I also like to thank the people in my group that have been involved in this work, especially one who did the calculations I've shown here. Of course, I'm also very thankful to everyone who provided funding for this work. And last but not least, I thank you for your attention. Thank you very much.